displacement gradient, material displacement gradient, Lagrangian description. You see, what do we mean by this? You see, we have the undeformed configuration, you see, or reference configuration. See, reference configuration. What do you mean that? You see, you have here a position vector x. This is position vector x, and there's a point, let's call P0. This is the initial, the undeformed, or the initial configuration here. This point P0, you see, you have here, this is the deformed, this is the deformed configuration, or current configuration. You see, there's a point P over here. So this is x, small x over here, this is small x, and this is u. Now this is a vector x over here. See, there's a vector x. Now u as a function of x. This is Lagrangian description. Why? Because this is the initial point. So the particle moves from P0 to P, okay? And so the reference, the initial point is at P0. So the material moves, you see, and reach point P. That we'll call material displacement. Now x is a position vector, okay, looking at this point P. This is a spatial, small x is a spatial coordinate, capital X is a material coordinate. Let's write here, x is the material position vector. Let's put this position vector. Okay, this is Lagrangian description. Now we want the displacement gradient. Okay, now let's start is this. So xi, let's put here small. The small x is equal capital X plus u. You see, look, the x plus u is a small x. Now, using a free index, xi is equal xi plus ui. See, for I is equal 1, 2, and 3. Now, delta xi is equal delta capital Xi plus delta ui. Now, let's see this variation with respect to the variation of the undeformed. Now, attention here. You see, this is x. This point here, okay, is x plus delta x. See, there's another point. You see, this point P0, let's call point Q0 over here. Now this x, this is delta x. This point here will be point Q. So this point P, this point Q. So delta x. Now let's see the gradient. You see, now delta xi delta capital Xj is equal, now delta xi delta xj plus delta ui delta xj. We want to calculate, okay, the variation of u, the displacement vector, with respect to the variation of p0 to q0. As q0 goes to 0, goes to p0, delta x goes to 0. So let's do the limit. You see, the limit as delta xj goes to 0, delta xi, delta xj is equal limit as delta xj goes to 0 of the right hand side. So this is delta xi, delta xj plus delta ui, delta xj. You see? Now, this here, if you remember, this side over here is Fij. You see? Because Fij is equal partial of xi respect to xj. You see, this is the deformation gradient. Let's put a word here before. Let's say here material. You see? Material. Why? Because the variation of small x, the spatial position vector with respect to the capital Xj. So the reference is according to this point P0 over here. So delta x goes to 0 here, not there. And now you see this limit here will be this here will be d xi d xj. You see, capital X and capital X. You see, and this is the definition of ui respect to xj. So this is the gradient, the displacement gradient. You see, now attention on this. Attention. You see, look, x1, x2, x3 are the coordinates, which is independent. They are independent. So, you see, derivative of x1 with respect to x1 is 1. Derivative of x1 with respect to x2 is 0 because they are independent. So let's put the partial here, partial derivative. Okay? Now, this is delta ij. You see, let's write here, delta ij. You see, this in general we called capital J ij. So, the material displacement gradient is partial derivative of ui with respect to xj. Knowing that, you see, in the Lagrangian description, this displacement vector is given. Let's write here, okay, on this place. Now, you see, Fij, the deformation gradient, material deformation gradient, is the conic delta plus partial of u respect to capital Xj. Now, what do you want? We want the displacement gradient, material displacement gradient, and I'd like to emphasize that this is material because the derivative in respect to capital Xj. Fij, the deformation gradient, material deformation gradient, is the conic delta plus partial of u respect to capital Xj. Now, what do you want? We want the displacement gradient, material displacement gradient, and I'd like to emphasize that this is material because the derivative in respect to capital Xj. So is the displacement, this is a gradient, the deformation Okay, deformation gradient minus delta ij, or capital J is F minus I. Now let's do, now suppose let's say x, let's put here x here, instead of being function of capital X, let's do here given u as a function of small x, instead of u function of capital X. This you call spatial displacement vector. Okay, let's find out that is the spatial displacement gradient. Displacement gradient, now a spatial displacement gradient, Eulerian description. Given the displacement vector, now here is a function, you see, a function of a small x. You see, there's a small x. See, this is a small x. This is capital X. Now, here is our focus. See, on the point P. Well, let's start. You see, x is equal capital X plus u. You see, in this case, u is a function of x, a small x. Now, delta, let's write using free index, this xi plus ui. Now, delta xi is equal delta capital Xi plus delta ui. So I is equal 1 or 2 or 3 are the components. Now let's see the variation with respect to small xj. This is equal this delta xi delta small xj plus partial of ui with respect to small xj. You see, this here is our focus. Now let's take the limit. As we did before, let's calculate the limit delta small xj goes to 0 of the left hand side delta xi delta xj is equal limit as delta xj goes to 0 of the sum of here delta xi delta xj plus delta ui delta xj. See, this is partial of xi respect to xj is equal now partial of capital xi xj plus partial of ui derivative, okay, partial derivative with respect to xj. Now since x1 x2 x3, see, these are the components of the position vector at P, since they are independent, this implies that delta xi delta xj is equal delta ij. See, partial derivative of x1 with respect to x1 is 1. Partial derivative of x1 with respect to x2 is 0, and so on. So this here is delta ij. This is delta ij. Now this is what you want. You see, you want the spatial displacement gradient. Let's call this as h. Let's put here, let's call k. okay, Kij. See? Now, attention, there's a partial derivative of the displacement vector with respect to the spatial coordinates, okay? And this over here, okay, I can remind you that this is f minus 1 ij, is the inverse of the deformation gradient. You see, this is capital Xi, small j. Let's call it as hij. You see, now you can write what you want. You want the displacement gradient, the spatial displacement gradient. So let's write right here. See, let's write here. So in the Eulerian description, we can express this Kij, you see, partial of ui respect to xj is equal, now this is delta ij minus hij. So this here is the inverse deformation gradient. Deformation gradient. See? And this is what I want. We want the spatial displacement gradient. Displacement gradient. See, that's it. Now, let's do an example, solve the problem in the next step. A displacement field is given by u as a function of capital X. You see, this is Lagrangian description. You see, u is a function of capital X is equal x1 x3 square e1 plus x1 square x2 e2 plus x2 square x3 e3. So the displacement field is written in the Lagrangian description because the function of capital X. I'd like for you to pay attention. This, I will not use it, but it's good for you to know that the same u is a function of small x. You see, just to emphasize, u doesn't change if I change capital X by small x. But we're not going to use this because we want to calculate using Lagrangian description. You see this f. Now, let's calculate directly the material displacement J. It's quite easy because J, let's put the partial of ui respect to capital Xj. This is equal, now I'll write down the matrix. So the partial of u1 respect to x1, partial of u1 respect to x2, partial u1 respect to x3. Here is partial of u2. You see, u1, u2, and u3 are the components of the displacement vector respect to x1, partial of u2 respect to x2, partial of u2 respect to x3. Now the third row, partial of u3 respect to x1, partial of u3 respect to x2, and partial of u3 respect to x3. Now this matrix I can write right here. You see, this is u1, this is U1. This is U2, and this is U3. You see? Now, partial of U1 with respect to x1. So here is x3 squared. You see? Now, partial U1 with respect to x2. So this is 0. Partial of U1 with respect to x3 will be 2x1 x3. So this will be 2x1 x3. Now, partial of U2 with respect to x1. You see, it will be, if this is x1 squared. So this will be 2x1 x2. You see? Partial of U2 with respect to x1. Now, partial of U2 with respect to x2. So this will be x1 squared. And partial of U2 with respect to x3, this will be 0. There is no x3 over here. Now partial of U3 with respect to x1, so this will be 0. Partial of U3 with respect to x2, see this x2 is squared, so this will be 2x2 x3. And partial of U3 with respect to x3, you see this will be x2 squared. x2 squared. Now, this is the matrix Jij. See, Jij. You see? This is the material displacement. The material displacement here. See, this is the material displacement. Now, we could use to calculate F, we could use this relation. J is equal F minus I. You see? So F is equal J plus I. Then always remember Fij is equal Jij plus delta Ij. You see, it'll be easy because we just add one here, and one here. That's F. So F is equal, now this will be, you see, delta Ij. This element here is first row, first column, 1, 1. So I add one here, 1 plus x3 squared. And the diagonal, let's write now, 0, now 2x1 x3. And here 2x1 x2. Now I'll add one over here because this is the second row, second column. I is equal, J is equal 2. So this is 1 plus x1 squared. This is 0. Here is 0. This is 2 x2 x3. And I'll add one here. Why? Because this is the third row and third column. I is equal, J is equal 3. So this is 1 plus x2 squared. This is F. Now, I would like you to pay attention what I'm going to say. Let's calculate F independently, knowing this J over here. You see, let's calculate F. The answer is already done. The answer, you see, is F and J. I calculate J and F. That's okay. But let's calculate F independently of knowing Jij, the matrix Jij. Let's calculate the material deformation gradient F. Don't forget Lagrange description. You see? Lagrange description, the matrix Fij is partial of small xi respect to capital Xj. The reference or the undeformed configuration. This is respect to capital X. Don't forget this. Now, we need X, so Xi, we don't know. You see here, we don't know. The displacement field U, or displacement vector U, is given, but we need Xi to do the partial derivative. So now we know that Xi is equal Xi plus Ui. You see? Now, X1, this implies, obviously, that X1 is equal capital X1 plus U1. X2 is equal capital X2 plus U2, and X3 is equal capital X3 plus U3. So this will be easy. Why? Because the vector X, are right down here. No, let's do this. You see, the vector X is equal, now the capital X plus U. So capital X will be X1 U1 plus X2 E2 plus X3 E3 plus U. Now X1 X3 is squared U1 plus X1 is squared X2 E2 plus X2 is squared X3 E3. This is equal. Now, you see, X1 E1. This will be X1 plus E1. You see, U1 is not U1 is X1, X3, U1, plus, now, you see, X2, E2, X1 is squared, X2, so this will be X2 plus X1 is squared, X2, E2. You see, I add E2 here and E2 over here. X2 plus X1 squared, X2. And the last one is X3, E3. X2 squared, X3, E3. So this is equal X3 plus X2 is squared, X3, E3. You see, now this is X1, this is X2, and this is X3. Now we are ready to write this matrix, the answer. So, and compare with this. You see, F here was calculated knowing capital J, knowing the displacement, material displacement here. So we are calculate F, okay, independently of J. You see, that's direct from this relation here. So let's do it. The answer is straightforward, because this will be, let's write here, x1 respect to x1, partial of x1 respect to x2, partial of x1 respect to x3. Now, partial x2 respect to x1, partial x2 respect to x2, partial x3 respect to x, this is 2, respect to x3. And here will be partial of x3 respect to x1, partial of x3 respect to x2, partial of x3 respect to x3. This is equal, you see? Now let's do the derivative, okay? Now here, I erase here and write. You just look, you see? This is equal, put 3 here. This is equal, now look. Derivative x1 respect to capital X1, this is 1, plus, now here is x3 is squared, because derivative x1 respect to x1 here is x3 squared. So this x3 is squared. Now, partial derivative x1 respect to x2, so this will be 0. Now, partial derivative x1 respect to x3, you have to be careful here, because here is, this is 0, and this x3 is squared, so this will be 2 x1 x3, you see? Now, partial derivative of x2 respect to capital X1. Be careful, there is a 2 over here, x1 is squared. So this will be 2 x1 x2, x1 x2. Now, partial derivative of x2 respect to x2, capital X2. You see, this is 1, and this is x1 is squared. So this is 1 plus x1 is squared. Now, partial of x2 respect to capital X3, so this will be 0. Now, the third row here is partial derivative x3 respect to x1, 0. Partial of x3 respect to x2. Be careful here. You see, x2 is squared, so this will be 2 x2 x3. And partial x3 respect to x3. This is 1 plus. Now this is x3 plus x2 squared. Now you can compare, you see, look. This here came from J is equal F minus I. You see, this here. See? And these were calculated independently of knowing J of